this was from the last part of chapter 6 stuff. So in each of these cases, you had to figure out what the bonds, the individual bonds in the molecule were, polar or nonpolar, and then you can decide if the positive side is on pieces on one side and the negative side pieces on the other side, then we would call that molecule polar. Otherwise, if everything's kind of symmetrically distributed, or you've got like negative on the outside and positive on the inside, that would be nonpolar. So let's take a look at this one. NF3, are the NF bonds polar or nonpolar? They're polar because the difference in electronegativity between N and F is about 1. So that's a pretty big difference. And then what about the overall molecule? Yeah, how do you know? Yeah, you could cut like right through the middle and all the F's are on the bottom and the N is on the top. So that means the negative stuff would be on the bottom, positive stuff's on the top. That's a polar situation. I don't know why my bubbles look different on here, but anyway. Okay, what about for this next one? Is a CO bond polar? CO is polar, right? Yeah. What about CH? CH is nonpolar, so this one has both. And then is the overall molecule going to be polar or nonpolar? Polar, because we've got the negative oxygen on top, the positive stuff on the bottom. You could draw a line and have negative on top, positive on the bottom. That's polar. And then what about for nitrogen? What is that bond? Bond's got to be nonpolar because it's the same atom on both sides. So the electrons aren't going to be pulled more to one side or the other. And then that's also the molecule, so that ends up being nonpolar as well. Okay. Write the formula, give the name of the following. So a little more practice, this time all together with the covalent stuff in there as well. Tin carbonate, that's going to be an ionic compound. Tin 2 plus tells us it is, or tin 2 tells us it's going to be 2 plus. We know carbonate. So the overall compound is like that, 2 plus, 2 minus. PF5, that fits in the covalent category because P and F are both over on the right side of that line. So that's phosphorus pentafluoride, right? Because we say that there's 5 of them there. So I wouldn't say phosphorus 5 because it's not a metal. And then finally, magnesium nitride. We know magnesium is +2. We know nitride is -3. So we've got to put those together in a compound. We get that. Okay. If you didn't get those, please keep working on it because all the equation stuff that we're going to be doing, that we just did, but that's going to be on the next quiz and the next exam and all that, is going to require that you are able to write down the formulas from the names. So please keep working on that, keep practicing that, because that's going to keep coming up. And then finally, what's the major type of attractive force that occurs between iodine molecules? What do we call that? You remember? So first of all, is iodine polar or nonpolar? It's got to be nonpolar, just like nitrogen, because it's got the same thing on both sides. So what are the types of forces that we have in nonpolar molecules? Remember? Dispersion forces. So that's what they're called. So make sure you know those different kinds of forces: dispersion forces, dipole forces, hydrogen bonding. Be able to identify those and how they affect things like boiling point. Sound good? Okay. Next quiz will be next week. You want to do Tuesday or Thursday? No preferences? Thursday? Thursday good for everybody? Okay. Next Thursday we'll do the next quiz, and that'll be over the chemical equation stuff. All right. Okay, so next, we've got a couple things to kind of finish up about chapter 7, about talking about reactions and equations. First thing we're going to look at is something called redox, which is short for reduction and oxidation. And this is a particular type of reaction. And so what we want to be able to do is identify when this type of reaction is happening. So you've probably heard at least the word oxidation before. We use it to refer to things like when metal oxidizes, like when it rusts. And because it has that term oxide in it, it sounds like reacting with oxygen. And that is true, that reacting with oxygen is a type of oxidation, but we actually define these terms a little bit more generally. And they apply to more things than just when we have oxygen. So reduction is defined as, whoops, not that. We get these things mixed up all the time. Reduction's defined as a gain of electrons. So for instance, we talked about ions, like when chlorine, which is just a neutral atom, gains electrons, it becomes chloride with a -1 charge. That's an example of reduction. Whenever you're going more negative or less positive, that's an example of reduction. So something like Cl2 going to Cl- is reduction because it's going from a charge of 0 to a charge of -1. So in order for that to happen, this had to gain, what's a plus? Gain 1 electron in order to do that. That's an example of reduction. Where we see that in an equation is wherever electrons are gained. So in, let's see, in one of the reactions that you did on Tuesday, if you remember, you put magnesium in some hydrochloric acid, and what happened? Remember? Put a little piece of magnesium in the hydrochloric acid. Yeah, it dissolved, like it bubbled and got hot. A bunch of bubbles came out. There was a little smoke. Does anybody remember that doing this? Yes, you all did it. I mean, I saw people do it. Yeah, so the rest of that reaction was that it formed MgCl2 and hydrogen gas. Okay. So this is what's known as a redox reaction, meaning that something is undergoing reduction, is gaining electrons, and something is undergoing oxidation, which is losing electrons. So I guess we should put that up there too. Oxidation. So if we had like sodium metal, it became sodium plus, that lost an electron because it went from neutral to +1, from 0 to +1. And that means that there must be an extra electron here that's come off there as one of the products that's come out. Now there's all kinds of rules for determining, not all kinds of rules, but there's rules for determining what kind of oxidation states different elements are in. That's why if you look at this periodic table, there's all these different numbers that sometimes are charges, but sometimes they're not. They're actually called oxidation states. And if you go on and take more chemistry, you'll learn how to calculate all the oxidation states. But for our purposes, what we're interested in is determining whether or not oxidation and reduction has happened. So have things lost electrons or have they gained electrons, and how do we know? So in a reaction like this, the most clear way that you can look for the existence of oxidation and reduction is to look for atoms that are in their elemental state. Okay. So the oxidation state, or the charge of a pure element, we're going to use this term oxidation state, which is not exactly the same as charge, but will work fine for us. Pure elements always have an oxidation state of 0. So if you have a reaction that has a pure element on one side, and then an element in a compound on the other side, you know that that can be classified as a redox reaction. You know that this has taken place because some electrons have gone from one thing to another thing. So in this case, we know that oxidation reduction has occurred because we have, let's look at the magnesium. Mg in its pure elemental state has an oxidation state of 0. What's the charge of magnesium on the other side? On the right side of the equation, what's the charge of magnesium?
0.
On the left side, it's 0. But what about on the right side? It's 2, because it's in the compound with chloride. We know chloride has a charge of -1, and magnesium gets a charge of +2 in magnesium chloride. So let's write that. In this reaction, magnesium starts as 0 and ends up as +2 in a compound with chlorine. So what does that mean has happened here? Is that an example of reduction or oxidation? Has magnesium lost electrons or gained electrons? Lost electrons, because it went from 0 to positive. So it's lost electrons. And that means that that is oxidation. So what do you think gained electrons? The hydrogen, yeah, because it was in a compound before, and now it's by itself. If it's in a compound, it usually has a non-zero charge. In HCl, does anybody know what the charge on hydrogen is in HCl? If you had to guess?
1.
Yeah, +1. It's actually a covalent compound, but it's an acid, and so when it dissolves, it becomes H+ and Cl-. So it's +1, but kind of a weird +1. But it goes from +1 to H2, which is 0. So if it's +1 to 0, that's an example of reduction. So do you sort of get that? Let's look at an example of a reaction and try to decide if it is oxidation or reduction or not. Let's look at another reaction from Tuesday. We took cobalt nitrate, cobalt-2 nitrate, reacted it with sodium hydroxide, and formed a cobalt hydroxide precipitate and sodium nitrate. Does anybody remember, was that the blue one or the purple one? The like turquoise one or the purple one? I don't remember. Okay, well anyway, it was one of those. It made that nicely colored precipitate. So is this reaction a redox reaction? Does it fit in this category of oxidation and reduction? And how do we figure that out? What do you think you would look for here first to determine this?
The charges.
Yeah, let's look at the charges. And mostly we're going to focus on the metals. It's true that nonmetals can change their oxidation state, but what we're going to see is mostly things about metals. So let's take the cobalt, for instance. Does the cobalt change its charge from the left side to the right side? It doesn't. How do you know?
It's +2 on both sides.
Yeah, because cobalt's one of those that can change its charge, so we have to be a little bit careful. But we can look at the ions that it's with and figure out if it's changed its charge or not. Nitrate is always -1. So if it's paired with 2 nitrates, that means it's got to be +2. Hydroxide's also -1. So if it's paired with 2 hydroxides, it's got to be +2. So cobalt stays +2 and +2. What about the sodium? Sodium change charge in this reaction? Take a look at it. Again, it doesn't. The only way sodium can ever change its charge is if it's just sodium by itself. Because whenever it's in a compound, it's always going to be +1. So if you've got a sodium compound on the left and a sodium compound on the right, okay, that's also not changing charge. So if we don't have any changing in charge, we don't have any movements of electrons. If we don't have any movement of electrons gaining or losing, then we would say this reaction does not fit in that category of a reduction, oxidation, or a redox reaction.
So we wouldn't look at the others?
Right. If nothing's happening with the metals, chances are nothing's happening with anything else either. In this case, we can also see that the ions don't change. So nitrate stays nitrate and hydroxide stays hydroxide. So that's another clue that nothing is really changing. Okay, so let's summarize this. So to look for redox, what we're going to do is first we're going to look for if neutral elements become compounds. And check, and then if that isn't there, we're going to check the charges for changes. In almost all of these reactions that you will see, if it fits into this redox category, you're going to see some neutral elements somewhere. That's not true of all reactions, but the other ones, organic compounds and things, are a little bit more difficult to check for oxidation states. We're not going to do that in this class. Okay, so here's another one. All I want you to do is tell me if this is a redox reaction or not. And we saw this one before. So is it a redox reaction? What do you think? There's no ions here, but we should still be able to figure that out. Does it have any of the characteristics of redox reactions, would you say? Maybe, yeah. What do you see?
The neutral elements became compound.
Yeah, neutral elements become a compound. So this is one where it's not easy to try to figure out the charges because there's no metals. There's no like, we can calculate it using some other techniques, but it's not easy to look for charges. But if we recognize that we've got neutral elements on the left and we've got a compound on the right, there has to be some change in electrons to make that happen. And that makes it a redox reaction. So by seeing neutral elements right here, we can say, yes, this is a redox reaction. Electrons are moving around from one side to the other. Okay, if we look at how that's done in the book, I think they go a little deeper into it. No, maybe not. So you may want to skip some of these, but let's take a look at some of the ones that they do talk about. Oh. All right, so these are all redox reactions. Let's see if we can figure out what is oxidized and what is reduced. So the first one, we've got lithium and fluorine going to lithium fluoride. How can you figure out what's oxidized and what's reduced? What would you look at first?
They're gaining or losing electrons.
Yeah, we want to know if they're gaining or losing electrons. So we have to look at the charges on the left and the charges on the right and see what the change is. So let's look at lithium first. Doesn't matter which one you do first. We'll look at lithium. What's the charge of lithium on the left of this equation? 0, because it's all by itself. It's not in a compound. And what is it on the right?
1.
+1, because it's in a compound. You see that? Okay, what about fluorine? What is it on the left? 0, right? It's by itself. And then on the right?
-1.
Yeah, that's when it's got its negative ion. So one is going from 0 to +1. One is going from 0 to -1. That's an example of, well, one of them is going to be oxidation, one of them is reduction. So which one is oxidized? Which one loses electrons? Lithium. 0 to +1 is a loss of electrons. And that means that fluorine is going to gain the electrons. You can't make electrons disappear in these reactions. So if once you determine that one thing has been oxidized, something else has to be reduced. Something else has to get those electrons that the other one has lost. Okay, let's look at one more. Let's look at C. You can go through the other ones on your own for homework, but let's look at C right now. Aluminum and tin ions, tin 2 becomes aluminum ions and tin. This one, we don't even have to calculate the charges. It's done for us, and we're not shown what the anions would be. We've got aluminum metal becoming aluminum ion. So is that an example of oxidation or reduction?
Oxidation.
That's oxidation. It's lost electrons. It's become more positive. That's oxidation, reduction. What about the tin? What's happening to that? So that because it's in the same reaction, we can say we know that's got to be the other one. That's got to be reduction. If we've got the one that's oxidation, the other one has to be reduction. And we can see that too. 2+ becoming 0 is gaining electrons. If it was missing 2 electrons and it gained those 2, then it becomes neutral. So that's how you do these types of things. Questions, concerns about that? You can do that. Again, as with everything, especially the equations from last week, it's all about practice. Even if you're looking at this and you think, yeah, I get it, make sure you go home and actually practice by doing the homework so that you're ready for the next quiz and exam. Okay, other thing we're going to talk about today is energy in chemical reactions. So you remember back a couple chapters ago, we talked about heat and energy, and we did some labs and did some reactions that got cold and some reactions that got hot and all of that stuff. So now we're going to define that a little bit more clearly and how we talk about stability of molecules, energy, and things like that. So in a chemical reaction, you've got some changes happening. Let's use our example that we've been using all the time, hydrogen and oxygen again. That's how we would express this reaction in an equation. But there's something else in here that we don't usually put in a reaction, but that's worth noting that it is actually there, and that is heat. So in this reaction, we could add heat to the right side of this equation, which you did, I think, in one of the labs. It said, what side of the equation would you add heat to? In this reaction, we'd add heat to the right side of the equation, showing that doing this reaction produces heat. So where does that heat come from? What does it mean that this reaction produces heat? Everyone's just sort of staring.
Doesn't breaking them apart take heat?
Yeah.
So adding them together produces heat?
Right, yeah. So that's where the heat comes from. If we go back to our diagram that we looked at before, we've got 2 hydrogen molecules, 1 oxygen molecule, and then 2 water molecules. So another way we can think about this reaction is 2 hydrogen-hydrogen bonds are breaking, and 1 oxygen-oxygen double bond is breaking. And then 4 hydrogen-oxygen bonds are forming. So all of those things are happening in this reaction. And the fact that heat is produced means that it takes more heat more heat is produced when those HO bonds form than is used when those other ones break. And we can look this up in a table. Over here. Maybe. If I can find it. Maybe not. No? Okay, we're not gonna look those up. We're just gonna talk about it then. So this tells us exactly that the energy that it takes to break those molecules up is less than the energy you get back by forming them, because the energy comes out. So if we were to plot this reaction on a graph, we make something called a reaction coordinate or reaction energy diagram. And it looks like this. The y-axis is energy. And the x-axis is reaction progress. So the reaction is progressing from left to right. It's starting on the left and then going to the right. In this particular reaction, we start with some reactants. Let's say we start with reactants at this energy level. And this would be the 2H2 plus O2. So that's our reactants. And then the reaction occurs, and we're left with the products, which is water. So are the products going to be at a lower energy or a higher energy than the reactants? Do we draw the products as being lower energy, like below that line, or higher energy above that line? And how do you know? is. Well, let's look at it. If heat is produced, if heat comes out, does that mean that our molecules have become more stable or less stable? Help at all thinking of it that way? Okay, perhaps not then. So the answer is the products are at a lower energy than the reactant. And the reason we know that is because heat comes out of the reaction. So heat is released to the surroundings. Remember we talked about the system and the surroundings? That means we started at this level of energy and we ended at this level of energy. Therefore, all that difference in energy must have come out and left onto the surroundings. So this tells us that we have an exothermic reaction. And the way that we would plot this is not a direct straight line, but something like this. We can learn a couple things from this. First of all, what we just talked about, this difference in energy between the reactants and the products, this tells us that because we went down from a higher energy to a lower energy, that's the energy released. So that's the energy released by the reaction, the difference between the energy of the reactants and the energy of the products. But something else is happening here. There's this little extra hump. It doesn't just go straight down from reactants to the products. Does anybody know what that hump is for? Why do we have to go up in energy before we go down?
Well, don't the bonds have to break apart before they join up?
Yeah, right. So we have to do something to kind of get this thing started, to start breaking up some bonds. Has anybody ever seen hydrogen gas? Actually, you have because you made it on Tuesday. When you did that thing with the metals going in the hydrochloric acid, the stuff that was bubbling out was hydrogen gas. And oxygen is in the air, right? So did it explode? It didn't. Did anybody's explode? I don't think so. But you have this mixture. You have this explosive mixture where they should have produced a whole bunch of heat and exploded if hydrogen and oxygen react with each other. So what prevented hydrogen and oxygen from reacting with each other when we did that reaction? So we all still have our hands and stuff. What prevented that? It was that we couldn't get over that hump. We didn't have enough energy to start the reaction. And that's why you can keep a bunch of hydrogen in your car, for instance. I mean, not like in your car, but if you had a hydrogen-fueled car, it would have a tank full of hydrogen in it that is not exploding, hopefully, even though there's lots of oxygen in the air. And that's because you need this little activation to actually get the thing started. So this difference in energy, the amount of energy that you have to give the reaction to get it started, is called the activation energy. And maybe we can actually try this one, unlike the sodium one. But if we fill the balloon with hydrogen and oxygen, the balloon wouldn't just instantly explode. But if I put a match up to it, it would explode. If I sparked it, it would explode. So a lot of times, that's what our activation energy is. It's to add heat in a particular way. If you think about fuel, like gasoline, gasoline's been sitting in the ground for millions, billions of years. Doesn't just explode, right? It doesn't just burn. You can put it in your car, doesn't burn. You can leave it out, doesn't burn. But as soon as it gets a spark, that's when it starts to burn. And so that's the activation energy that produces the reaction. And once the reaction gets started, because it's exothermic, it is releasing its own energy, and that's enough to keep activating more and more bits of it. And that's why when it starts to burn, it keeps burning. So that's an example of an exothermic reaction. Let's look at an endothermic reaction as well. An endothermic reaction would have the opposite thing happening. So the reactants might be here. And then the products would be higher energy. There's still going to be an activation energy to an endothermic reaction. But overall, if we look at that same energy difference, the change in energy has gone upwards. So the change in energy is positive instead of negative. And that's energy that's been absorbed in the course of the reaction. So this is a reaction that would feel cold to the touch because it's absorbed energy from the surroundings, from the solvent, from the air, from your hand, whatever. An exothermic reaction is going to look like that. Or an endothermic reaction, sorry. You can also have multi-step reactions. A multi-step reaction might look like this. So you could have something that looked like this, which is still going to be overall what? Is this exothermic or endothermic overall? Yeah, this is exothermic because the energy is being released. You're going down to a lower energy. But this is an example of a reaction that has some intermediates, and it has to get do some other stuff before it gets from reactants to products. And there's all kinds of different ways that can happen. Label this here. It's a multi-step reaction. So we still have reactants here, stuff we would mix together. Products are what we would get down here. And then these things would be called intermediates. Okay. Something that kind of goes along with this, but has some important differences, is what we call rates of reaction. How fast does a reaction go? How rapidly do reactants turn into products? The rate is related to the activation energy. And that makes it a little bit confusing sometimes. But let's look at two different exothermic reactions that have the same starting and ending point. We'll have one kind of like what we drew before. And then we'll have a new one that goes like this. So these two reactions are both exothermic. They're both losing energy, giving off energy to the surroundings, going from high energy to lower energy. The only thing that's changing is the activation energy. The red curve, sorry if you're colorblind, the one that's going higher, has a higher hill. The first one I drew has a higher hill. And that tells us that it takes more energy to get it started. Whereas the green one has the lower hill, which means it takes less energy to get started. So more activation energy means slower. And less activation energy is faster. So the activation energy controls the rate, and that's sometimes not totally intuitive, because if you think of a reaction like burning fuel, burning gas, we think of that as being a fast reaction. You light it up and it burns. But if it's happening on its own without that activation energy, it's actually kind of slow, because that stuff just sits in the ground and doesn't do anything for a really, really long time. So reactions with high activation energy, we can't judge slower or faster based on like our experience of how long it takes. We have to think about the activation energy and think about how much energy it takes. And this becomes really important with something called catalysts. Have you heard the term catalyst before? Anybody know what a catalyst does?
Like reduces the energy needed.
Yeah, it reduces the activation energy. A catalyst reduces activation energy which speeds up the reaction. And the way it does that is by allowing it to go a different path, allowing it to go through a different path. So if we had a reaction that went like this, that's like our standard reaction, again, an exothermic reaction. The catalyzed one might have more steps, but the steps would have lower activation energy, and so it would end up being faster. So this is an example of one without a catalyst. And this is one with the catalyst. That's really important in processes in our body. Anybody know what the catalysts in our body are called? Enzymes, yeah, right. So without those, you have all these things, all these reactions happening, these electron transfers, oxidation reduction stuff that's required to make us go. And those would be way too slow, and nothing would happen. You wouldn't be able to metabolize your food and all that stuff. So if you have these enzymes, these catalysts, then it brings the activation energy down, speeds up the reaction, allows it to happen. So when we say that somebody like if you're lactose intolerant and you lack a particular enzyme to break down those proteins in, that sugar, lactose, what that enzyme really is a catalyst that makes that reaction go faster so that it's processed. Yeah.
What would be some examples of like the steps it would take? Like the one with the catalyst has a lot more of the curve. So like what would be those steps?
It's different for a lot of reactions, but let's say for instance, two molecules, because this happens, two molecules have to come together in a particular orientation in order to react. So they have to go like this and like this to react. And because they're just swirling around in solution, they're not always going to do that just randomly. So let's say an enzyme comes along that locks one thing in one position and then locks the other thing in the other position. That's two more steps, because the first step, it has to react with the enzyme. The second step, the other thing has to react with its enzyme, and then the two things have to come together to react. So that's like two more steps, two extra steps. But then when they approach each other, they're exactly lined up. So the extra steps allow it to actually go faster because it corrects for that orientation or something. Does that kind of make sense? Yeah. So that's how extra steps could do that. It's not a very specific example, but I'm trying to hide the fact that I don't really know anything about biology. So I'm just pretending that I know. If we talk to people upstairs, they'd probably be like, oh, here's a bunch of good examples. Okay, let's see if I think we got everything. Oh, okay. So one last thing that I didn't really talk about. So what affects the rate of reaction? thinking about those things we were just talking about, number one thing, well, I mean, all these things affect rate of reaction, but one thing is concentration of reactants. If you have a greater concentration, you usually increase the rate because it allows those reactants to have greater contact with each other. This is all about molecules bumping into each other in exactly the right way. So the more you can increase that possibility of that happening, the more you increase the rate. So if you put higher concentration in there, that means you've got more stuff bumping into each other, and that's going to increase your rate. Okay. Second thing, the surface area or the particle size of the reactants. I mentioned when we were talking about reaction types and stuff like that and the little states that we don't see a lot of reactions between solids and solids. And that's because of this. Because molecules need to be, and atoms need to be in really close contact to react with each other. If you have two solids, even if you grind them really, really well, if the particle size is still not that small from the standpoint of a molecule. So only the surfaces of the two little pieces are going to be touching. That's the only place that the reaction can happen. The only time solids react very well is if one of them starts to kind of melt as the reaction is happening, or if you grind them with special equipment to make sure that the pieces are super, 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 super small. But usually we need to dissolve our reactants to get them to react. And that's because that allows them to separate from each other in the solid state. In solution, they're going to be separated, and then they can combine and actually react with each other. So greater surface area or smaller pieces also gives us a higher rate. And then the last one that we already talked about is the presence of a catalyst. So if there is a catalyst and it is there, that can increase the rate as well. We should also note that a catalyst is generally not consumed in the reaction. I guess we'll put that back up here when we defined catalyst. So usually you only need a tiny bit of catalyst because it regenerates in the course of the reaction. So it helps some things react, then it's good, it's by itself again, helps some more things react, helps some more things react. So you usually don't need as much of it. That's not always true, but you usually don't need as much of it because it is regenerated. So that's how you affect the rate of your reaction. That's how you can speed things up. Questions about that stuff? All right, we got about 10 minutes left. Let's do one equation problem, and then we'll be done. Actually, let's do this first. This is how I would ask, because I always like to give examples of what a question would look like about topics that we just talked about. So here's our reaction. Nitrogen oxide reacting with hydrogen gas, forming nitrogen. So first of all, would you consider this a redox reaction or no? Got some head nods. Yeah, how do you know it's a redox reaction?
It's a pure element and then it's in a compound.
Yeah, you got an element going to a compound and then a compound going to an element. So hydrogen becomes water and NO becomes N2. So yes, that's a redox reaction. It might be difficult to determine which one is being oxidized and which one's being reduced here because it's hard to calculate the charges from what we've done, but we can at least recognize that it is a redox reaction. All right, so how do we affect the rate if we do these different things? If we add some NO, what happens to the rate? Does it go up, down, or no change? How many people say the rate goes up? Rate goes down? Rate doesn't change? Just not answering. Yeah, the rate goes up. So that would go under number 1 here. We've increased the amount of reactant there by adding NO. And that should increase the rate. Now that's a guess. It's a guess based on information that we know. Some reactions don't depend on the concentration of one reactant or the other because of the mechanism by which they do their reaction. So in some cases, you could add more reactant and it doesn't change the rate. But we don't know that without actually doing the reaction and checking it. So we could guess, yes, that's going to raise the rate. What about lowering the temperature? What do you think that's going to do? Slow it down? Why? You're right.
Because it is heat activated.
Yeah, we've lowered the temperature, so we've decreased the amount of energy that's available for activation. In fact, we should actually list that as a 4th thing here. Increasing the temperature gives more energy available for the reaction, and so that's going to increase the rate as well. What about removing some hydrogen gas? What does that do to the rate?
Lower it.
Yep, that's going to slow it down because now we're taking reactant out, and assuming the rate depends on both reactants, that's going to slow it down. And then finally, adding a catalyst speeds it up, and that's always going to be the case. Catalysts are really important because of this decreasing the activation energy. There are some processes that are just too energy intensive to be useful in various ways, either to our bodies or like environmentally. And so developing a catalyst that can do something with much less energy can be really, really important. If we think of some of the big high energy things that we have to do, one of the biggest ones is taking nitrogen out of the air and making it into ammonia. So reacting the nitrogen in the air with hydrogen and making ammonia. That's an extremely energy intense process. It takes a whole lot of energy to do that. And we do use a catalyst to do that. And it's one of the biggest, I think it's the largest chemical reaction in the world, like the most done chemical reaction in the world, because that's what we need to do for fertilizer. So basically all agriculture depends on that reaction happening. And it takes a lot of energy to do that. So, so there's a lot of research being done to try to find alternative catalysts that could reduce the amount of energy that it takes to do that reaction. And that could greatly decrease the cost of growing food, which is important to do. And there's a lot of examples of things like that as well. All right, questions about that? Okay, that should pretty much finish up that chapter. So we'll have a quiz next Thursday. Please be practicing these equations and things, because that's a big part of, that will be a big part of the next exam too, which is in a few weeks. And have a good weekend, full of chemistry practice. Yeah. Yeah, like there? Yeah, that's fine. Thanks.
My ADP teacher used, like she was talking about us.
Yeah.
Or talking about enzymes to us.
Uh-huh.
And she used the example of like doors in the stadium. So if you have to get 1,000 people out of the stadium, it's helping them more doors. And she just used that. I don't know.
That's a good way to think about it. Yeah, that works.
Biology.
But what?
Biology kind of.
Then people will really think I understand biology, so that'll be a good one.